Hello Year 10 and welcome to my lesson on nuclear decay equations. Before we start the lesson, let's make sure you're fully equipped for it. So you're obviously going to need paper to write your work on, pen, pencil and a ruler. And for today's lesson, you will need a periodic table. I know we're doing physics, but yes, we do need a periodic table. I've attached a periodic table to this lesson in form of PDF. So either open that, print it off, or if you've got a periodic table in a textbook or something, have that open. But if you're going to use a periodic table in a textbook, just check that it's got these bottom two rows. So to get yourself ready, can you pause the video now? Right, so you should be ready to start. So first things first, let's get a lesson title, Nuclear Decay Equations, and your work dated. Okay, here's your starter task. So just a quick reminder, if you see a yellow star on a slide, that probably means I'm going to ask you to pause the video to get some work done, but you will always have a task to do on any slide with a yellow star. Here's your starter. It's based on radioactive half-life that you did last lesson. Have a go at it now. Pause the video. Let's have a look at the answers, see how you got on. Now that first question asks you to consider a radioactive source with a half-life of 15 minutes. You're told that its initial count is 240 counts per minute, and you're asked to work out what the count would be after 1 hour. The way to approach this is you need to work out how many half-lives have occurred. So 1 hour is 60 minutes. If a half-life is 15 minutes, 60 divided by 15 gives you 4 half-lives. Your radioactive count then of 240 will have halved 4 times, leaving you with a radioactive count of 15. The next question says you've got a radioactive source with an initial count of 16 counts per minute, and after 2 hours it's decreased to 4 counts per minute, and you're asked to determine the half-life. Thought process here should be that 16 has halved twice in that time. So it's gone from 16 to 8 and then 8 to 4 in 2 hours, making the half-life 1 hour. Final question. If you've got an activity of 32, and remember that BQ stands for becquerel, and that's the unit of radioactivity or counts per second. It doesn't matter what unit we're using, same rules apply. So if I've got 32 becquerels, after how many half-lives would the activity have dropped to 4? Thinking about it, 32 has halved 3 times in that time, so 3 half-lives have elapsed. The other activity you had to learn about in your half-life lesson was looking at a half-life decay curve. So if we look at this graph, it's got activity on the y-axis, that's this one over here, and it's got time on the x-axis. And you're asked to determine the half-life of iodine 131. Can I just remind you this 131 here is the mass number of that isotope. So have a look at it, pause the video. Do you know how to work it out? I'm hoping you worked it out in this way. If half-life means the length of time it takes for the activity to drop to half, 100 up here was your original activity, so dropping down to 50 is halving that activity. And if we draw a line across from 50 to the curve, we can then draw a second one down to the time scale here, and that tells us that iodine 131 has a half-life of approximately 192 hours. That's roughly 8 days. Here's another half-life curve. This one, it's a different isotope of iodine 135. Work out the half-life from this one. Pause the video, have a go. So drawing our line across at 50 and down to that scale, reading the time scale there, you should have worked out that that has a half-life of 7 hours. So that's just double checking that you were okay with last lesson. Now, before we move on, let's do a quick check on critical knowledge. You've got 5 questions there that you need to know the answer to. I'd like you to have a go, so pause the video now. Now, also on this slide, you've got that quick reminder of, have you got that periodic table sorted? How did you get on with the prior knowledge? What does the atomic or proton number tell you about an atom? Well, it defines the element. Remember, all atoms of the same element have the same proton number. And remember, on a periodic table, that's the number in the bottom of the box underneath the nuclear symbol. What does the mass number tell you about an atom? Well, that tells you the total number of subatomic particles in the nucleus, and it's always the sum of the protons and the neutrons. As physicists, we're really interested in isotopes because they have some strange properties, but you need to remember that if I refer to isotope, it's atoms of the same element with a different mass number. So if we look inside the nucleus, that means it must have the same number of protons, but a different number of neutrons. Finally, before we move on, alpha particle, remember that's 2 protons and 2 neutrons released from the nucleus of a radioactive nuclei. And a beta particle, this one was a bit strange. This one is where a neutron in the nucleus breaks down, leaving behind a proton, but releasing an electron. So you should have already written down today's title, which is the decay equations. And I'm hoping by the end of today's lesson, you would be able to confidently write balanced equations to show alpha decay and balanced equations to show beta decay. Moving forward then, beta decay. Remember, that's when an alpha particle consisting of 2 protons and neutrons is shot out of a radioactive nuclei. Sometimes it's referred to as a helium nucleus, but for today's lesson, we're just going to be working with it as an alpha particle. Now, if a nucleus emits an alpha particle, it loses 2 protons and 2 neutrons from the nucleus, and so that means a new element is formed. If we're going to represent that as an equation, you can see a nuclear decay equation for alpha decay in the middle of your screen now. Look carefully at it and see if you can answer the questions. What will happen to the mass number of an atom if it throws out an alpha particle? What will happen to the atomic number? Have a think about it, pause the video. Well, I'm hoping you've noticed that mass number on the left-hand side has decreased by 4 and the proton number has decreased by 2. So the number of protons has changed, and this means we've made a new element. Hence, if I use my little pointer here, the nuclear symbol is changed. It was uranium, now it's TH, that stands for thorium. But what you'll also see is there's this alpha particle written here on my equation as well. That alpha particle is critical to make sure that this alpha decay equation is balanced. Look at the equation. Are you happy that it's balanced? Pause the video if you need to consider it. You should have noticed that the mass numbers of these 2 things on the right-hand side here add up to 238, which is the original mass number. And also the atomic number here, 92 and 2, add up to the original atomic number. That makes sure that my equation is balanced. Now you're going to be asked to write nuclear decay equations, and they're unlikely to give you all of the information in the question. So I've got a question here, or a statement up the top here. Americanium to equation. You're going to be asked to write the equation for that, so I'm going to take you through it in steps. Now, the first to remember is this 241 here is the number of that atom, and we need to use that in the question. So let's work through it. Step 1, write down the nuclear symbol for americanium. You're going to need to go to your periodic table to find it. Americanium has a mass number of 241 and a proton number of 95, and there's its symbol in the middle there. So using my periodic table, I've got more americanium. I then write down the mass number and proton number of the element formed when the alpha particle is emitted. So my top number has dropped by 4 and my bottom number has dropped by 2. Using my periodic table, I've gone and found the symbol for the new element. So I looked up number 93 and found it was neptunium, and so that's NP. I've now finished off my equation by writing that alpha particle so that my two mass numbers, when they add up together, gives me the original, and my two proton numbers, when I add them together, give me the original. Okay, it's your turn to have a go on your own. You've got 5 radioactive nuclei stated there, and they're all going to decay by alpha emission. So stop the video, pause the video, have a go, write the full equations for me, please, and restart when you're ready. Now, I'm not going to go through the answers to these ones because this is the work I'd need you to upload to Teams so I can check your understanding. We're going to do the same idea now with beta decay. Now remember, beta decay is that high energy electron that is spat out by the nucleus when a neutron turns into a proton staying behind in the nucleus. So if we're going to have a look at nuclear decay equations, it's important that we understand why they're written in the way they are. So it's really important that you understand in this case the mass number stays the same and the atomic number goes up 1. And that beta symbol there, we need to understand why it's got a mass number of 0 and an atomic number of -1. Pause the video, have a think about it. So if you've had a look at it, remember no particle with mass is lost from the nucleus during this reaction, only that tiny little electron that doesn't weigh anything compared to the nucleus, and so the mass number stays the same. But when a neutron breaks down, shooting out that electron, it leaves behind a proton. So we've gone from 6 protons in the original to 7 in the new one. So we've made a new element again. Now, the rules of balancing an equation means the mass numbers on the left-hand side must equal to the mass numbers on the right-hand side, and the same for the proton number. So if we have a look at it, the mass numbers added together, 14 plus 0, gives us our original 14. But when we look at that bottom row, the atomic numbers, we need to make sure that that 7 on the right-hand side added together to the proton number of a beta particle equals 6. And the only way I can do that is to give the beta particle a -1, because it's not a proton. It can't have a mass number, and so it's got that -1. Using the same process of alpha decay, you can learn very easily how to write balanced equations for beta. So same thing, we're going to start with Americanium-241. So we've written down its mass number, its proton number, its nuclear symbol. Now this time it's beta decay, so the mass number stays the same, and the proton number goes up by 1, so it's now 96. Using my periodic table, I go and find the element with the atomic number of 96, and I write it down. So we've got the Cm here. And we finish off our equation with that beta particle to make sure it's balanced. Okay, your turn to have a go on your own. So remember, mass number stays the same, proton number goes up, and you're going to need that periodic table. Pause the video, complete this task for me. Before we finish, just a couple of things to remind you about. You only need to be able to write decay equations for alpha and beta decay, even though you learned that there were 4 different types in a previous lesson. Remember, the types of decay are alpha, beta, gamma, and neutron. Now, gamma radiation is part of the electromagnetic spectrum. It's not a particle at all, and so it has no effect on the nucleus of the atom in terms of its particles, so we cannot write an equation for it. Nothing changes, it stays the same. No new element, no equation. When it comes to neutron decay, that one's a little bit more complex, and you don't study the nuclear decay equation for that until A-level physics. So for nuclear decay, you just need to know it happens when it's a neutron, not the equation. That's the end of today's lesson. You've got work you need to upload to Teams for me, so make sure it's nice and clear and ready for me to be able to give feedback from. So pause the video and get ready to upload your work to Teams.